Okay, welcome back, students. So this is going to be just working through section 19.2 from your book, teaching you both understanding and procedure. And the view of this is that it will help you revise or indeed to study independently. So we'll jump straight into section 19.2, which is about mapping diagrams. So straight away I want to just show you what a mapping diagram looks like visually. This is the mapping diagram. Okay, and we're going to just go through the book line by line. It's important to, like, reading mathematics is not a simple process, and it's important that you become independent readers. So I'm just going to support you with that here. So I'm going to go through line by line, word by word. So I always use a ruler to help me read for understanding. Consider this function machine where you multiply by 3 and subtract by 4. If we, sorry, it does say if, we will input all of these numbers. So they're talking about a set of inputs. The name of the set of inputs is the domain. It's the set on the left where the arrows moving to the output. Okay. So we have that the set of input numbers or any other types of inputs is called the domain of the function. The set of outputs is called the range. Now we want to be careful here, that's great, but we also use the word range in statistics where we go max, take away min. That's not what this means. So we need to be careful that in the case of functions, range has a different meaning than it has in the case of statistics. Okay, here range means the output set. Now also an area for confusion is the difference between functions that take in discrete values or like integers or natural numbers with gaps, and functions that are continuous to take in an infinite number. So these are finite sets because there's only 5 inputs, or sorry, can I count? I can't. 5 inputs, and there's exactly 5 outputs as we would expect, because for every input there should be 1 output. Okay. Just a little thing to qualify that. As far as I know, like 3 could have also gone to -1, so it could be less in the range, but we'll see that and we'll learn that as we work through it. So my terminology, continuing to read carefully, we're back here. I don't want to skip anything. The input numbers and output numbers can be represented by a special type of diagram. So when you put your domain set together with your range set and you map the input to the output with the arrow, then you have a mapping diagram, which is what this entire thing is here. Okay, where the domain set is given and the output numbers are given. Okay, each input number is mapped onto its output number. In the mapping diagram above, notice that there is one and only one output number for each input number. So that's important. It's highlighted. It's bolded up for a reason. For every input number, there is exactly one output number. And we could start playing devil's advocate. It'll be probably done for us down here, but I could just start kind of thinking mathematically and thinking, what does that mean? And it's always good to think about showing a non-example. Okay, so we know what an example looks like, but what will break the rule? Okay, let's say we have our domain, and let's just think this here is going to be the range, and this, so let's just drop 2 points in here, and let's say he went there and he went there. That would be an absolute no-no. That is not allowed. Okay, because for one input you have 2 outputs, and that's very confusing. What value should I give? So f of x, or the output, should always be 1 value. Now this is allowed, so that is not allowed. Okay, 2 emanating from one place in the domain is not allowed. What is allowed is 2 arriving in. Okay, in the range 2 can arrive in. This is allowed because it's very clear that the output of this input value or element is this element. Now I'm using the word elements because it's sets, and the output of this is this. For instance, the squaring function, 25. If I put 5 into a squaring function, I'd get 25. But if I put minus 5 into the squaring function, I'd get 25. Okay? If we flip that around backwards with a square root function, we're in trouble. Okay, so a square root function is not a function. It has this square root property that we've mentioned in class. Okay, we move on. In mathematics, we use the word function for any rule that produces one output value for each input value. Okay, so now we're moving on, and we're still in section 19.2 to notation for a function. So consider this rule for a function: double the number and add 4. Great. And what does it look like mathematically? The expression is 2x plus 4. Okay, the notation is f of x equals 2x plus 4, where x is really the entire domain. It can be the entire domain. Now some other functions, some other notation that we need to know is that f maps x, and you see this arrow, it's a bit like those arrows here. It takes x and it produces 2x plus 4. Okay, f maps x onto 2x plus 4. And you could take a numerical example. F would map 3 onto 2 3s plus 4. Okay, it's not very popular, but it is because most students much prefer this f of x equals 2x plus 4. So this is the one we're going to favor, but we do need to be able to read this and understand it. So what I was saying to you is, the minute you see this, you can convert it into its f of bracket, f of x notation, and then you can continue from there. That's what you're going to see most often. Okay, and we can also recall that because f of x is plotted up the way and x is plotted out the way, then if we to think coordinate geometry, then we often say, well, we'll call that y. So that's what's going on here. So y equals 2x plus 4, where it looks like we have two variables, but they're dependent on each other, where y is determined by x because it has a graph. Okay, great. So now we come to the tricky little thing called the codomain. I mean, you would think we had it all sorted because we have our domain and we have our range, but now there's this expression, the codomain. So let's carefully read the book for understanding here. So we're taking these two sets, fine, it's plotting them here, and we're seeing that not all of the of this, which I think is going to be called a codomain, is in the range. Okay, so basically you might say, well, why have a codomain? Why bother putting in numbers that aren't there? Well, it makes life easy for us, and we don't have to think through everything. Okay, so you might say, for example, I'll just give you an example so that we can jump right down to it. So x squared, what does it do? Well, we might say it maps the natural numbers onto the natural numbers without specifying any of them. So that would mean, well, we'd end up getting, you could say, well, all the natural numbers are in here, but we can see no natural number gets mapped when you square it to 2 or 3. So they would not be part of the range, but they could be part of our codomain as we defined it loosely, because we didn't want to put too much effort into describing only the range. So the codomain, let me put it this way, the range is a subset of the codomain. Now, there's a lot of hand waving going on, as you can see here, and so we'll need to bed that down and spend time working on the words. Let's see what it says here. I hope it agrees with what I said. The set of inputs is called the domain. Excellent. The set of outputs is called the range. Excellent. I'm happy with that. The set of possible outcomes, where we decide what's possible, like the natural numbers are mapped onto the natural numbers through squaring, through f of x equals x squared, creates this codomain, which encompasses at least all our domain and often a lot more. Okay, so the set B is called a codomain. The set of all possible outcomes is called a codomain, but the actual real outcomes are called a range. Just one other reason you would use this might be that before doing an experiment, you don't really know what's going to come out. So what are the ages of students in the classroom? You walk into the classroom, what age are you? 11, 12. You don't know, so you would just say, my domain is n, very loosely. then during the actual experiment, when you walk into the class, you'd find 11-year-olds and 12-year-olds and maybe 13-year-olds, but you might say, no, there's no 14-year-olds, so 14 would get left there. Okay, so then 14 would be in the codomain, but not in the range. I hope you could follow that. Right, so here's an example. Going to work through it. The function is defined, okay, with this mapping notation. So I would say to you straight away, say, well, that's the exact same as this. The domain is 0, 1, 2, 3, 4. That's very important. We're going to use all of them. Represent f on a mapping diagram and write out the couples generated. And then what is the range of f? Okay. So let's keep covering up. Okay, let me take that off picture. And I suggest you do the same. So you'd work through this problem yourself, and then just agree with what they've got. Represent f on a mapping diagram. Okay, so we have our domain. Check that in picture, and we have our 0, 1, 2, 3, and 4 in that domain set. We are going to map each one using f of x equals 3x minus 2. So treble and take 2. Treble 3, take 2. 6 by trebling, take 2, 4. 9, 3 is 9, take 2, 7. 12, take 2 is 10. And we can give that in list form like we would in sets. We could say this, the range is -2, 1, 4, sorry, -2, 1, 4, 7, and 10. Okay, and they've used a table very nicely, and then they give the couples. So this is a new thing. So what are the couples? The couples, the list of couples is a set in its own right. So the couples are, so if it's a set in its own right, so they said the couples are, and they went like this. So it's a set, and it's a set of input-output pairs, like an x and a y value, really. Okay, like that. I'm not going to fit them in there, but there's nothing wrong with going down the way to make things easier for me. Like that. 2 is coupled with 4. Notice how I used the word coupled there as well. So these are couples, and 3 is coupled with 7. It's a round bracket, and 4. So couples are incidents of what went in and what came out. Okay. Now, identifying functions. Still on under one section. Back in the picture. I must say these are longer than I thought. About time I made these for you, and we can do these in class as well. When a function is represented by a mapping diagram, each element of the domain maps onto one and only one element of the range. We've been talking about that already. Consider these two mapping diagrams. Yeah, we talked about this earlier. Is B allowed to map to two places? Absolutely not. This is not a function. It is a relation, by the way. So a relation is a more general thing, but a function will not allow this. But this is allowed, and it's probably a squaring function that we're looking at here. This is good. This is not good. So diagram 1 is not a function since the element B is paired with two elements. You're not allowed pair domain elements to more than one. Okay. You are allowed to not map it to anything. I think. might know some. Okay, maybe that's not true either. We do say every element in the domain has one and only one output. So scratch that. Look, mistakes can be made. I'm not going to restart the video again, that's for sure. So every domain element has one and only one output. But that is happening here. So we are allowed to have the lines meet at the range, but not have the lines meet at the domain. It's this bit here that's not allowed. This is allowed. Okay. We have already seen that a function, so that's our identifying functions and identifying non-functions. Couples. We have already seen that a function can be written as a set of couples or ordered pairs. Now the order does not, when we say the word order there, we're not talking about the order of these. We're talking about that these are in order, you cannot swap them. In notation form, a couple or ordered pair is written as x mapped to y. If we're to use the function notation, we say x is mapped to f of x. So this is what a couple looks like as long as we've defined f of x. When a function is written as a set of couples, no two distinct couples will have the same input. Okay, so the first numbers are not allowed to be the same. So, sorry, I went off the picture there, that wasn't great. So the first numbers have to be unique. So you could scan across here and see, oh no, I wouldn't like that because you cannot have the 2 3s. Okay, so that's breaking the rule, and you have a visual way of learning that. Great, we've come to the end of the section. I'm going to park that video, it's 16 minutes long, and then we're going to work our way through 19.2, the exercises, because I think that'll just give you a better chance to break up and plan your independent learning. Okay, students, as always, I'll see you in the next one.